So last class I asked you guys to that before you go to bed you should try and solve a couple of problems. I don't know how many of you did those. I asked you guys to do at least 5 mechanisms before you sleep. You know, so huh? No, I just said it when I was teaching. I just said it that you should do 5 mechanisms before you sleep, so that you don't forget. You know, because if you don't do those mechanisms before you sleep, you will forget. If you do them before you sleep, you will dream about them. Okay? And life will be easier. So, I just want to see those who did it by putting out this problem here as a challenge. So if I give you this compound, the one I just drew on the board, reacting with HBr, what would be the product? What would the product of this reaction? In order to do it, try to solve this by going through the mechanism, by providing the mechanism. And then tell me what you think the product will be. Want to try that, Miles? Yeah. Just try to get involved. Everyone should get involved, because if you just sit and wait for the answer, trust me, it will not help. You know, you can get involved by trying yourself, by telling to your neighbor and talking to your neighbor, you know. Just try to get involved. Because if you just sit and wait for me to do it, when I do, it always looks easy, but it is not. Right? Yeah, when the teacher knows it is easy, but then when you do it, it's like nightmare. Yes, for the one in the right. Okay. So just try to do those mechanisms. Just try it and see. Remember I said you should do how many mechanisms before you go to bed? Yes. And you don't study before you sleep. Who proved that? I'm a scientist too, so it is true. Look, you've never noticed that when you dream, most of the time is the last thing you were thinking before you sleep. Is it true? No, I don't believe that. Is that true or not? Like, most of your dream is usually the last stuff you thought about before you sleep. Half of the time, right? Yeah. You see? In French, there's this saying, la nuit porte conseil. I don't know how to say it in English. La nuit porte conseil. I will try to translate it in English. That, well, usually when you are in trouble, they say, if you go to bed and come back the next morning, you probably find a solution to your problem. I don't know how to say that in English. La nuit porte conseil. Yeah, conseil is advice. So that literally it means night gives you advice. If I want to translate it the way it is. But I don't think that that's how to say it in English. Yeah. So it means that in French, basically what that means, like when I say night gives you advice, which is a literal translation from French. It means that when you go to bed, you probably dream about it and then see a solution to the problem. So, Alisa, instead of doing just 5, you can now do 10 problems per night. Trust me, you'll only be dreaming about chemistry. Yeah, you'll only be dreaming about chemistry. So I will leave you guys with this problem and then we'll continue our class. We'll come back to the problem when time comes, okay? We'll come back and talk the solution to this problem when it is time. When it is time. If you didn't have this answer, if you didn't have this as your structure, I will not explain why for now. For now, I will not worry why this is the answer, but just believe me, okay? Just believe that I'm right. This is a CH3. That will be the answer. Can you guys see it? I don't know if you can see. Can you guys see from here? Let's see. Yes. For now, just believe that this is the answer. If we didn't have this answer, then we'll talk about it in the future. Let's continue from where we stopped. You remember this reaction energy coordinate diagram, right? Where over here we have the reactant, and over here we have the product, and up here we have a transition state. So when you convert something from a reactant to a product, you go through a transition state. If that's a one-step reaction. And now, structures with similar energies. Structures with similar energies, I would say species with similar energies have similar structures, basically. So if you look at the reaction potential, if you're looking at a molecule here, okay, where I have that my blue dot, that molecule there will have a structure similar to that of the reactant. Does that make sense? The blue dot, which you see over there, will have a structure similar to that of the reactant. The red dots will probably have their structures similar to that of the product because they are closer in energy to the product. Does that make sense? They are closer in energy to the product. So that's basically what we want us to do. And that is what we refer to as the Hammond postulate. That's the Hammond postulate. So if you look at a transition state of a mechanism, of a reaction mechanism, if you look at a transition state of a reaction mechanism, the structure of the transition state will be similar to the structure of the closest intermediate. Does that make sense? The structure of the transition state will be closer to the structure of the closest intermediate. When you say the closest intermediate, what do you mean? Well, you remember that when you have a two-step reaction, there is an intermediate in a two-step reaction, right? So, for example, if I have a reaction like this is a two-step reaction. I don't know. Can you guys see it? Yes. That's a two-step reaction. This is my intermediate over here. That's the intermediate. So this transition state here, the structure of that transition state will be very similar to its closest intermediate, which is that one. It will not be similar to that of the reactant, it will not be similar to that of the product, but it will be similar to that of this intermediate. Okay? Which other one? We only have one intermediate in this one. So look, if I draw an energy diagram like this, okay, remember this is the reactant, that's the intermediate, and that's the product. Does that make sense? Reactant, intermediate, product. Then we have two transition states, which I guess you guys know. Now, this transition state here, the one with the star, with the asterisk, okay, the structure of that transition state will be very similar to the structure of I, the intermediate, because it is closer in energy to I. Does that make sense? Which is also true with this guy here. The structure of the intermediate with the blue star will be closer to that of the intermediate I, because they have about the same energy. Does that make sense? Yes. So both of your transitions are both going to be like equally close to I? Well, similar in structure, okay, to I. Similar in structure to I, compared to R and P. You know, we are comparing I to R and P. Is that because like they're bonding changes in two transition states? Well, in transition state, you always have bond changing. Bonds are being broken and bonds are being formed in the transition state. That's what is happening in the transition state. Okay, so for an exergonic reaction, you know what that hexagonic reaction is. In an hexagonic reaction, the product is more stable than the reactant. So a reaction like this one here, the transition state will resemble the reactant. That makes sense, right? This is my transition state. You see the transition state is closer in energy to the reactant. So in an hexagonic reaction, transition state is closer to the reactant in terms of structure. And then in an endergonic reaction, the transition state will be similar to the structure of a product. Okay? And so sometimes you will hear us talking about an early transition state versus a late transition state. Does that make sense? So when we talk of an early transition state, we are referring to a transition state that resembles the reactant. Meaning we're talking about a transition state of an hexagonic reaction. And when we talk about a late transition state, we are looking at a transition state that resembles the product, which is a transition state of an endergonic reaction. Does that make sense? Okay. And understanding these things give us an idea why the tertiary carbocations are the preferred path whenever you're doing a reaction with the alkene. Okay, we'll get into more details. Okay. Now, remember last class we talked about rate of reaction. We said reactions that goes through the formation of a tertiary carbocation is generally faster compared to that goes through a secondary or a primary. And the reason we gave was because the tertiary carbocation was more stable. Does that make sense? We said the tertiary carbocation was more stable. So the more stable your intermediate is, the more stable your intermediate is, chances are that your reaction will be faster. Does that make sense? Chances are that the reaction will be faster. Remember, I am talking about the intermediate. Does that make sense? Stability of the intermediate. Let's come back to this reaction coordinate diagram, the one in red. Look at that reaction coordinate diagram, and I want us to examine that reaction coordinate diagram. Okay? The distance here. What is that distance called? This the one I marked in blue. How is that distance called? We gave a name to that. Yeah, but it has a special name. Gracias, mucho gracias. Say it again. Perfectly perfect. So that's the activation energy. Okay? That energy difference is the activation energy. And what did we say about the activation energy? Can anyone remind us? How does activation energy affect the speed of a reaction? What's the relationship between activation energy and the speed of a reaction and the rate of a reaction? The greater the activation energy, the slower the reaction. Does that make sense? That's exactly what he's saying. The greater the activation energy, the slower the reaction. Okay? Now, one thing we talked about already, we mentioned something already, that the more stable the intermediate. So I'm bringing in something new again. The more stable the intermediate, this I, the faster the reaction also. Does that make sense? The more stable, yeah, meaning lower in energy. The more stable the I, the faster the intermediate. The faster the reaction, yes.
So the intermediate and the carbocation are the same thing?
Yes, in the chemistry of alkenes, our intermediate is the carbocation. So in that case, that's why tertiary carbocation, the reactions are faster compared to secondary and primary. So the more stable the intermediate, the faster the reaction. Okay. Now, I want to find out from you guys, which other way, when you look at that reaction diagram, which other way do you think can be done in terms of playing with the energy to make the reaction faster? What do you think we can do here? Say that again. Oh, well, we've talked about that already. You know, the lower the intermediate in terms of energy, the faster the reaction. What else can we do for the reaction to be faster? Huh? Well, yeah, if you add a catalyst, what does the catalyst do? Any idea? It lowers the, okay, yes, it lowers the activation energy by, okay, yeah, you see, you guys are talking chemistry now. You guys are talking chemistry. So, if you lower the energy of the transition state by putting a catalyst, meaning that you make this energy get a little bit lower, using a catalyst, chances are that that reaction will move faster. Does that make sense? Now, so we've talked about two ways of making a reaction faster. You can have a stable intermediate, or you can lower the transition state energy, maybe by using a catalyst. There is a third way we can do it. Can anyone see it? How else can we make a reaction go faster? If you look at that diagram, how else? No, we've talked about the intermediate already. We've talked about the transition state. We said if we have a stable, let me recall. We talked about the intermediate. We said if we have a stable intermediate, then the reaction will be faster. If we lower the transition state, the reaction will be faster. So there is one last thing that you guys are missing. What else? What else? What else? Look at that diagram and tell me, what else can we do? What can we do to the reactor? We raise the reactor. Does that make sense? We raise the reactor. So, if we take this reactor and make it a little bit higher, you see it will reduce that energy difference between the reactor and the product. We raise the reactor. And raising the reactor, what are we doing to the reactor? No, we are raising the reactor. So, huh? No, remember, she said raise the energy of the reactor. So what does that mean in terms of stability? Less stable. Does that make sense? Is it okay, guys? No, but we'll come to it. We'll come to it. Yes, we'll get to that. We'll get to that. Yes.
Wait, so raising the reactants makes it less stable, not more stable.
Raising the reactant energy makes the reactant less stable. Okay? Makes the reactant less stable. But by doing that, by making the reactant less stable, you make the reaction to go faster. Yes. At the end of the day, we're only looking for means to lower the activation energy. Does that make sense? We can lower the activation energy by lowering the transition state energy, or by increasing the energy of the reactor. Does that make sense? We can increase the energy of the reactor, meaning that if we have a less stable reactor will react faster than a more stable reactor. Does that make sense? A less stable reactor will react faster than a more stable reactor. But then in terms of intermediate, please take note. Reactant intermediate is the opposite. In terms of intermediate, a more stable intermediate will cause the reaction to be faster compared to a less stable intermediate. Does that make sense? I don't want you guys to mix them up. Is that okay? So in terms of rate of reaction, in terms of speed of reaction, less stable reactants react faster than more stable reactants. Lowering the more stable intermediate makes the reaction move faster compared to a less stable intermediate. Does that make sense? And we'll look at that into details. We'll talk about it a little bit. Are we good with that? Yeah. So, that's why in this case, if you look at the molecule we have here, which is 1-propene, this is 1-propene, and we react the 1-propene with HCl, two things can happen. We can have an intermediate which is a secondary carbocation, and we can have an intermediate that is a primary carbocation. Okay? The intermediate with the secondary carbocation is more stable than the intermediate with the primary carbocation, and so only the product formed as a result of a secondary carbocation will be observed. The primary carbocation almost does not form. Okay, usually you will hardly form. In short, as from today, I will tell you guys that forget about primary carbocation as intermediate. Okay, you will hardly form it as an intermediate, hardly. And even if you form it, something will happen to it, and we'll talk about that something very soon. Even if you form it, something will happen to it. Now, the speed at which you form those carbocation also matters. The speed at which you form the carbocation also determines how much product you will form in your reaction. Okay? And the speed at which you form carbocation depends again on the stability of the carbocation. So it will be faster to form a tertiary carbocation compared to forming a primary carbocation. If you look at the structure that we have down here, if you look at this molecule down here, if you want to do the mechanism, because remember I told you, the more mechanism that you do, the better for your health. Okay, so if we have this molecule and we decide to do the mechanism for that molecule, the electron will start from the double bond to the hydrogen and this one breaks. So when that happens, you now have your intermediate, which will be a CH3 that will be your intermediate. Okay, and this intermediate is a tertiary carbocation. That's what leads to the formation of this product. You can have another intermediate in which the positive charge will be on this carbon and the hydrogen will be connected on the other carbon. Is that okay? And that will lead to the product that will not be observed. So this product will not be observed because it goes through the formation of a primary carbocation. Are we good, guys? Let's skip that one. It's the same thing. So, remember the law we talked about on Tuesday. The more hydrogen you have, more hydrogen will be given to you. Remember we talked about it, we said it's a Markovnikov law. So the same law applies here. That's basically what we explain here with the law. So if you have asymmetrical alkenes reacting, okay, chances are that you might end up forming two products. One of the product will be a major and then the other one will be a minor. How do you know which one is a major? The major product will be formed as a result of having a more stable intermediate, carbocation. And that follows the rule that we refer to as the Markovnikov rule. Okay? That's basically the Markovnikov rule. The hydrogen or the electrophile, because remember the hydrogen is the electrophile. The electrophile will add to the sp2 carbons with more hydrogens. That's the rule. The electrophile, in this case the hydrogen plus the proton, will add to the sp2 carbon with more hydrogen. That's basically the rule. So if I look at this structure here, the two sp2 carbon, I have this guy here in blue and I have this other guy here in red. Those are my two sp2 carbon. The blue one is connected to one hydrogen, whereas the red carbon is connected to zero hydrogen. Does that make sense? So according to Markovnikov's rule, my major product will go, the hydrogen will go to the blue carbon. Does that make sense? So when I draw my major product, even without doing the mechanism, the hydrogen will be connected to the blue carbon. And over here, we have the red carbon, and over here we have the blue carbon. And so you notice that with the major product, the blue carbon has an increase of an extra hydrogen. Does that make sense? And the iodine now will be connected to the other one. With the minor product, this is the blue and this is the red. So this is minor because it doesn't follow the rule. And if you do the mechanism, which I will still ask you guys to do it on your own, you will notice that the major product goes through the formation of a tertiary carbocation. Does that make sense? The same story with the structure we have below. Same story with the structure we have below. In this structure, that is the red carbon, and this is the blue carbon. And so the hydrogen will be connected. The hydrogen will be connected to the blue carbon this time around. Does that make sense? The hydrogen will be added to the blue carbon, so we have a missing hydrogen here. And then the bromine will add to the other carbon. Does that make sense? Major and minor. Now, this is what we refer to as radioselectivity. So if you see this word, then that's what we refer to as radioselectivity. So radioselectivity means you form one product in preference of the other constitutional isomer. If you notice, both of them are constitutional isomers. Okay? We have constitutional isomers. So radioselectivity is the formation of one constitutional isomer over the other. Okay? The preference in the formation of one constitutional isomer over the other. That's basically what we refer to as radioselectivity. Okay? Are we good with that? With radioselectivity. So in this case, I will preferentially form this constitutional isomer over that one. So this reaction is said to be radioselective. Does that make sense? The reaction is said to be radioselective. And so radioselective reactions can be classified. We can classify them. There are some reactions that we say are highly radioselective or completely radioselective. In that case, you are forming 100% of one isomer and 0% of the other isomer. Does that make sense? In that case, you say, okay, this is highly radioselective. Then there are some reactions that are moderately radioselective. You know, you can form maybe 60-40%. That's like kind of moderate radioselectivity. And there are some reactions that are not radioselective at all. In that case, you are forming 50% of the product. So you have two isomers, you form 50% of isomer A, 50% of isomer B. In that case, that reaction is not radioselective. Does that make sense? Okay, so, but there's no cutoff number. There's no cutoff number to say this is what is required to be this type of selectivity. No. Okay, there is no cutoff. But if we look at the first reaction over here, we observe only this product. This product is not formed. So I will most likely say that this reaction is very selective, radioselective, right? Highly radioselective or completely radioselective, because I form one over the other only. But if you look at the second reaction, I have a major product and I have a minor product. Yeah, you see the selectivity starts to dangle. The radioselectivity starts to dangle. Okay? And each time I write this reaction, I want you guys to be able to imagine the mechanism in your head. I want you guys to be able to see that for the first reaction, this goes through a tertiary carbocation and this goes through a primary carbocation. I want you guys to be able to see. And can you guys see it? Yes. You see the chlorine is connected to a tertiary carbon. That's how I know that it goes through a tertiary carbocation. Does that make sense? Here it is connected to a primary carbon. That's how I know that the intermediate was a primary carbocation. Is that okay? So over here, what's the intermediate? Tertiary, right? And over here, what's the intermediate? Secondary. Does that make sense? Okay. So this will be secondary, and that will be a primary. Oops. Oh man, Zico. I think I need to go home early today. No, not now. After class. After class. Does that make sense, guys? And we said when a reaction gives you about equal amount of product, then the reaction is not selective. And you guys can tell me why this reaction is not selective. Why is this reaction not selective? Because they go through the same type of intermediate, right? Do you see that? They all go through secondary intermediate. Oh, by the way, when I put this zero on the top, it doesn't mean to the power zero, okay? It means secondary for me. So this will be my primary, that will be my secondary, and that will be my tertiary. Okay, it doesn't mean something to the power zero. That's just the way I write it shorthanded. So does that make sense now? So you've seen that secondary, intermediate, both of them. If both of them goes through the same type of intermediate, chances are that it will not be selected. Does that make sense? If one goes through a tertiary intermediate and one goes through a primary intermediate, you see, it doesn't match. You can't compare. It's like playing what is it? Toronto Raptors versus HU Pirates. Does that make sense? Like the NBA champs, Toronto Raptors versus HU Pirates is comparing the tertiary to a primary. You know, probably it would be like what would be the score? I don't know, 120 to what? 40? No, not up to 500. I don't think HU Pirate are that bad. So maybe 120 to 40. I don't know. So you guys understand. You guys understand what we're talking about. How that stability of the intermediate can determine how much product can be formed. That's the most important. And so if you believe that you understand it, then prove it. Okay? Prove it. This would lead to two problems. There are two problems. So finish the first one, then I will move to that. It's the same scan code. That will lead to two problems. Okay, so finish the first problem, and then we'll talk also about the second problem. So that should take a couple of minutes. So to answer this problem, you need to be also good with nomenclature. So you have to draw your structure first. That's how I will test your knowledge of nomenclature in the exam. I will hardly draw a structure and ask you to name it. Okay? So that will be part of nomenclature. Oh yeah, no, not only like 35 minutes. Yeah, it's like a week. Yeah. So you're like roughly 7 miles a day.
But we run 6 days a week.
Okay, so 6 35 by 6. That gives you what, roughly 6 miles a day. Because 6 is 36. So roughly 6 miles a day. That's crazy. That would be like about almost 15 kilometers per day. But you multiply by 1.6. Oh, almost 14 or 13 to 14 kilometers per day.
It's 9.6 kilometers a day.
9.6 kilometers.
Yeah, so 6
Oh, yes, 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 yes. Oh, I thought it was 2.6 miles per kilometer per mile. It's 1.6. Now they are roughly 10 kilometers per day. How many?
Really often to be precise.
2 miles.
If you walk around the
Zero.
campus, it
Huh?
should be at least 10 miles a day.
Oh yeah, yeah, that don't go out really well. I walk.
No, even walking is good.
I mean, I walk. So how we get to one?
So, let's look at it, guys. One methyl cyclohexane. So it is cyclohexane. So we have a cyclo, and it says hexene. So hexene, you put the double bond anywhere on the ring. Okay, we are drawing the structure because it's a cyclohex. That's the cyclohex, and the zine, we put the double bond anywhere on the ring. And then it says it is a one metal. So the structure says one metal. So the metal group should be on position number 1. And according to the rule, you also want the double bond to have the lowest number. So your one metal will be here. Does that make sense? Or you can also decide to make your one metal here. Those are the only two options you can do for the one metal. Does that make sense? Yeah, those are the only two options. If you decided to put your double bond here, the only options you have for the one metal is either here or here. Does that make sense? So everything depends on where you put your double bond. So let's leave the double bond there and let's leave the one metal over there. Okay, and we'll react that one metal with HBr. I react the one metal with HBr. And according to my mechanism, it's true I didn't ask you to do the mechanism, but if you know, I will keep doing it so that you guys familiarize yourself with it. If I do my mechanism, that's what I have. I will have two options as my intermediate, and I will draw the two intermediates here. So the first intermediate I can have over here is the guy with a positive charge over there, or I can have this other intermediate here with a positive charge over here. Do you see that? I don't know if you guys can see very well. So I will have the blue intermediate with a positive charge here, and the red intermediate with a positive charge there. Does that make sense? Those are the two intermediates. And so if I follow the red intermediate, my final product with the red intermediate would be this guy. And if I follow the blue intermediate, my final product with the blue intermediate would be this guy. The blue intermediate is tertiary. The red intermediate is secondary. Then the question says we should predict the major product. So I guess the major product will be the one formed from the blue intermediate. Does that make sense? Which is that one. And so we need to give a name to that product. We need to give a name to that product. And I guess the name will be 1-bromo, 1-methyl cyclohexane. Is that okay? It will be 1-bromo, 1-methyl cyclohexane. Yes.
How do you know it's just a double bond?
You could, when you first draw the ring, from the nomenclature, if we start again with the nomenclature, here, cyclohexane. Cyclohex, I know it's a 6-member ring. Then that zine, I can put the double bond anywhere for now. I can decide to put the double bond there. But then now I need to attach the one metal. The one metal can only be attached to the sp2 carbon. Okay? So with this particular case, I can either put it here or put it there. Does that make sense? And then from there you continue the same token. You will always lead to the same answer. Now the next problem. Here. Which of the following compounds react most rapidly with HCl? Which of them react most rapidly with HCl? So these are all reactants. So here we have to take note. Think about what we said earlier on. Earlier on we said The less stable the reactant, the faster the reaction. We talked about it, right? The less stable the reactant, the faster the reaction. And then we also talked about something else. The more stable the intermediate, the faster the reaction. So those are the two principles you need to keep in mind in order to answer this question. Does that make sense? So the two principles you need to keep in mind in order to answer this question. And so let's do it. Let's start with structure number 5. Let's look at the intermediates. These are the two carbons of interest. Okay? With those two carbons of interest, we can have two types of intermediates. And I want you guys to be able to see it. Here, I can have a secondary versus a primary intermediate. Does that make sense? I can have a secondary versus a primary intermediate. Okay? Who cannot see that? Hey, who is blind? Who cannot see that? Who's blind? Who cannot see it? Means everyone can see it, right? Great. Everyone can see it. So let's look at structure 4. What are the two types of intermediate in structure 4? I want an answer from somebody at the back. Somebody at the back. What are the intermediates for structure number 4? Are they primary, secondary, or tertiary? No one at the back? Secondary, right? Thank you. So this will be secondary and this will be secondary. Remember, this carbon atom here technically is a secondary carbon atom. It's connected to two other carbons. So if you are a secondary carbon atom, then you will form a secondary intermediate. Does that make sense? That's how I know it. That's how I know it. If I look at structure 3, this is a secondary carbon because it's connected to two other carbons. So the intermediate will most likely be, oh God. So with structure 3, the intermediate will most likely be secondary. Does that make sense? Structure 2, what do you think the intermediates will be? Tertiary, secondary. Tertiary, secondary, right? What about structure 1? Primary and tertiary. Now, in terms of stability of intermediate, we can now proceed by elimination. Remember, for a faster reaction, we said you should form a more stable intermediate. So by using the idea of stability of intermediate, we can delete these guys. 3, 4, 5. 1 and 2, we select 1 and 2 simply because they can all form tertiary carbocation. Does that make sense? They can all form tertiary intermediate. So that's what we want. But then now we need to distinguish between 1 and 2. Oops. Ah, this is the answer. Oh, Dr. Zico. Wow, God. It's okay. It's okay. It's okay. That's fine. That's fine. So does that make sense? Why we will have to eliminate 3, 4, 5? Yeah, we're getting to A. We're getting to why is it A. Remember, we said there are two things. We mentioned two things here that will determine the speed of the reaction. We said 1, the intermediate must be a stable one. And then 2, the reactant should be less stable. If you can destabilize the reactant, then you will cause the reaction also to go faster. And you said it, not me. You. It came from your mouth. Yeah. Does that make sense? So, in terms of stability of intermediate, we'll eliminate 3, 4, 5. Now, 1 and 2 is now the stability of the reactant. It turns out that 1 is more stable than 2 is. Oh, sorry. 1 is less stable than 2 is. Stability of alkenes. Okay? In terms of stability of alkenes, the more substituted the sp2 carbons are, the more stable the alkene. Does that make sense? The more substituted the sp2, you know what I mean by sp2 carbons, right? The carbons that form the double bond. The carbons involved in the formation of the double bond, those are the sp2 carbons. So, these guys here. So, in this case, these are my sp2 carbons. These are the sp2 carbons. These are the sp2, these are the sp2, those are the sp2. So the more substituted the sp2 carbon, the more stable the molecule is. And so if you look at this one, this sp2 carbon here, it is more substituted compared to this one. If you look at this, carbon, carbon, and you look at this one, there is a carbon and then one hydrogen. Whereas here, you have carbon, carbon, hydrogen, hydrogen. So you have more hydrogens here than there. Does that make sense? So one is less stable compared to two. And so if one is less stable, it means it will be higher in energy, but they still go through the same type of transition state. I mean the same type of intermediate. Does that make sense? 1 and 2, they all go through transition state tertiary, intermediate tertiary. But then, 1 is higher in energy than 2 is. So it will be easier for 1 to get there before 2. Does that make sense? Or is it like speaking Obara? Okay, great. So that's the way I want you guys to be able to apply this kind of knowledge, okay? That's the way I want you guys to be able to apply that. Yes, sorry.
Can you explain one more time how two more substituted?
You remember we said the more substituted, the more stable. In other words, you can also think about it reversibly, okay? The fewer the number of hydrogens in a double bond, the more stable the molecule is. That's another way of putting it, okay? Maybe that's the easiest way to see it. The fewer the number of hydrogens in a double bond, the more stable the structure is. So if I have structure 1, over here, there are hydrogens. And with structure 2, this is a hydrogen. And you see, in that double bond area, structure 2 only has 1 hydrogen, whereas structure 1 has 2 hydrogens. And so structure 2 is more stable than structure 1. So you can define that stability in terms of more substituted, more stable, or you can also say the fewer the hydrogen, the more stable. It all depends on the way you want to look at it. Does that make sense? Are we on the same wavelength, guys? Yes. And then, the less stable the reactant, the faster the reaction. The more stable the intermediate, the faster the reaction. Those are the things I want you guys to be able to apply, because you will need those concepts in order to answer your questions. Okay. Are we good, guys? Perfectly perfect. Now, we are basically done with, how would I say, studying the basic principle of the mechanism. Now we are looking into reaction. Okay. Those are kind of like the basic principle of mechanism. Now we're looking into the reaction. Now, what happens if we react an alkene with water in the presence of an acid, the product? Now, what we want you guys to keep in mind is, always ask yourself, who is my electrophile? Where is my electrophile? Because the reaction here is a nucleophile reacting with an electrophile. Your nucleophile is always the alkene, always the alkene. But then, your ability to know what the electrophile is important. Okay, who is the electrophile? So this is the reaction of an alkene with water. Okay, if you do a reaction without the presence of an acid, the reaction doesn't work. But once you add an acid, the reaction works. Once you add the acid, the reaction works. And so adding the acid is what we refer to as acid catalyzed. So the acid is the catalyst. The acid is acting as a catalyst. Does that make sense? We'll look at the mechanism. We'll look at the mechanism very soon. Okay. And so when you react an alkene with water and an acid, you form an alcohol. Okay. So in the alkene reacting with water and an acid will give you an alcohol. So that's the alcohol. And I want you to take note that the highlighted group, the OH and the H, that's basically water that you've added to the double bond. Do you see that? So you simply break the pi bond and then replace that pi bond with the OH and the H. Remember, OH and H, that's what gives you water molecule.
You said water and an acid?
Yeah, but the acid is a catalyst. So, yeah.
Okay.
But at the end of the day, what you are adding onto this double bond is a molecule of water. Remember, water is H2O. So we have the OH and the H. So technically, at the end of the day, remember, this is water. So you're adding the OH and the H. But then again, I want you guys to observe. I want you guys to be able to see. Where is the OH adding? The OH is adding to specific carbon. It's adding to the more substituted carbon. And then the H is added to the less substituted carbon. It follows the Markovnikov rule. You remember the Markovnikov rule. Those who have more shall be given. So this is my alkene. He has more hydrogen, and more hydrogen was given. Does that make sense? So those who have more shall be given. You have more hydrogen is given. Is that okay? Who can guess what will be on the next slide? Hallelujah. The mechanism will be on the next slide. The mechanism will be on the next slide. Okay. Now, whenever you're doing an acid catalyzed mechanism, take note. The first step ever, this mechanism is very similar to what we've been doing before. But the difference is that the first step is always a protonation. So you always have to add the hydrogen first. You add the hydrogen first. So I will zoom on it so that we can all see. Remember I said the most important is to determine who is your electrophile. And so this is sulfuric acid. This is my acid. So one of the hydrogens of the acid is the one acting as the electrophile. So the double bond attacks the hydrogen of the acid. That's my electrophile. To now give my intermediate. That's how we form that intermediate, okay? So first step, that's it. And then you form the intermediate. This is that intermediate here, the carbocation. Once you have the carbocation, that's where the water molecule now connects. Does that make sense? Guys, don't look at it as a picture. Do it. Practice it. Understand it. Then take more exercises, take more examples, and look at it. There is no way you will know it if you don't take a piece of paper and a pen and do it. I'm telling you, there is no way you will know it if you don't take a piece of paper and a pen or a pencil and do it. Do it the first time, you fail it. Do it the second time, you fail it. Trust me, the third time, you will not fail it. The third time, you will not fail it. Right, Alicia? What? Keep trying. Keep trying. I did that several times. That's why I know it. There's no way you will look at it and know it. No. No. So once the water molecule connects, okay, the last step is the regeneration of the acid. Remember we said this is an acid catalyzed reaction. The acid is a catalyst. And like every catalyst, you speed the rate of the reaction, but you are not used. So if I use the acid at the beginning, I have to generate the acid somewhere. I have to regenerate it. Does that make sense? So the last step of that now will be the regeneration of your acid. Now, one thing I want you guys to know, there will be different ways in which we'll be denoting the acid here. We can denote the acid as H3O+. That is an acid, so you will be seeing H3O+. Carelessly, we can represent the acid as H+, or we can represent the acid by its full formula. For example, HCl will be represented that way. Sulfuric acid will be represented this way. Okay, but all of them, most of the time you will see it as H3O plus. If you see H3O plus, know that it is an acid. Does that make sense? If you see H3O plus, know that it's an acid. So instead of having this, I could decide to have it as a H like this. Oh, sorry. I could decide to put it that way. In that case, I will have my double bond attack this and attack that one. So it all means the same thing. Does that make sense? So if you check, it all means the same thing. That's the first thing I want to draw your attention to. Now, the second thing I want to draw your attention to are the steps for the mechanism. Okay? The first step of the mechanism is what we refer to as protonation. Does that make sense? Meaning your alkene is protonated by the acids. That's the first step of the mechanism. The second step of the mechanism is nucleophilic attack. That's the second step of the mechanism. My first step is here. That's the protonation, meaning the alkene is protonated. So protonation to form the intermediate. Let me put it there so that it will be clear. To form the cation. Then the second step will be nucleophilic attack of the cation, which is here. The nucleophilic attack of the cation. That's it. Okay. So the water molecule now attacks the cation. Does that make sense? The water molecule now attacks the cation. And then the third step, generation of the acid. That's the third step. You regenerate the acid, which is what is happening here. You are regenerating the acid. Does that make sense? That's the third step. And those third steps are summarized here. Addition of the electrophile, which is what I call protonation. Then the second step is addition of the nucleophile, which is what I call nucleophilic attack. And then the third step is the water removes or regenerating the acid, which is what I call regeneration of the acid. Those are the three steps. Does that make sense? For an acid catalyzed reaction. So this was acid catalyzed reaction, addition of water. The same, I have 10 minutes, great. The same is exactly true for the acid catalyzed addition of an alcohol. Everything I said, yes. Yes.
So does this just fall under the category of electrophilic addition, or is this like a different?
No, those are all electrophilic addition.
Okay.
So these are like all the steps that happen during this electrophilic addition. Does that make sense? Yeah, these are like all the individual steps that happen for electrophilic addition to take place.
So does that mean all of the rules from before still apply to this, including the
Yes, yes. Because remember that all the rules we did was mentioning the cation, the stability of the cation. Does that make sense? That's what we're talking before, stability of the cation. Okay. So for the addition of an alcohol, please, it's exactly the same as the addition of water. The mechanism is exactly the same. Nothing changes. Does that make sense? So if you understand the addition of water, there's no reason why you should not understand the addition of the alcohol. Because your water molecule is written as this, right? That's the water molecule. Okay? And so your alcohol will be written as that. No, let me not write it that way. Let me not write it that way. Your alcohol will be written as That would be your alcohol. I prefer to write it this way. So do you see the similarity between them? The OH of water is simply replaced with OR. Does that make sense? That's it. That's just the difference. The OH is replaced by the OR. So anything that works for water is the same thing with the alcohol. So over here, this is your alcohol, and then look at what you're adding at the end. Remember with the first one we did, you had an H here instead of CH3. Okay? And this is an example of what we call an ether. So addition of water produces an alcohol. Addition of an alcohol produces an ether. Does that make sense? And the mechanism remains the same. So because the mechanism remains the same, which is what we have here, I want you guys to try it. Because I want you guys to do it. Feel free. Show me the mechanism for this one. Show me the mechanism for this one. And feel free to flip back to the previous mechanism you did, and do it. Okay? Go ahead and do the mechanism. Do it. Everyone should do it. Everyone should do the mechanism. If anyone doing the mechanism, then I will stop the class. If not, I will use my time to 9:15. Yeah, because I need to explain it. So do this mechanism. Feel free to go back and check what you have copied, what we did before, okay? That's the only way, I repeat, that's the only way we'll be able to master it. That's the only way we'll be able to master it. Okay, so I have it written down here. So let's quickly go through it. So the first step, like I said, is the protonation. Okay, you see, I've written my acid this way because I also want to familiarize myself with that. So the first step is the protonation. The double bond attacks the hydrogen from the acids. Okay, and so that leads to the formation of the carbocation. What? This guy here, this is H3O2 plus. Remember I said H3O, H3O is the same thing as the catalyst, right? It's the same thing as the acid. Because they're all the same, and I just want you guys to familiarize yourself with any of them. Does that make sense? They're all the same. Huh? They're doing CH3. This guy here is the same as this. Your name is Jakira. It's the same as Miss Patsy. It's the same people, right? So, yeah, I'm saying it because I don't want you guys to be confused. One day you see H3O plus and then you start asking yourself, what is it? Trust me, most of the time that's the one you will be seeing, H3O plus, especially when you'll be taking your exams out of this place. You understand what I mean? Because you hardly see people write it as H2SO4. Hardly. You mostly see it as H3O plus. And I want you to think about it. Now when you see H3O plus, it's the same as saying H2SO4, it's the same as saying HCl. It's the same as just saying H plus.
Yeah, we wasn't talking about the H2SO4. We were assuming that we were supposed to add the CH3OH.
Yeah, this is the first step, right? This is the first step that leads to the formation of your intermediates. This is your intermediate here. And now the intermediate is attacked by the alcohol. Does that make sense? So to create that intermediate, you use the acid to create the intermediate. That's the job of the acid. Once you've created the intermediate, that's where the alcohol or your water molecule, depending on which reaction you're doing, will now attack. Does that make sense? Okay. So let me go back to the original one. Here. Original one. First step. First step. That's it. Does that make sense? Use the alkene to create your intermediate. Use the alkene and the acid to create the intermediate. So once you have that, that's the intermediate over there. Now that's where the alcohol comes in the second step. If you're doing a water catalyzed, then you will use water. If you're using alcohol, that's where you use the alcohol in the second step. And the alcohol comes in the second step. And the third step, you are regenerating your acid. So you are eliminating that proton. I want you guys to take note. The positive charge, I want to see it. You see here, oxygen is having a positive charge because oxygen is connected to three groups, three bonds. There is a bond here, there is a bond there, and there is a bond here. So when oxygen has three bonds, it needs to have a positive charge, formal charge. You remember that? And then you now have your final product. This is another way of writing the acid. I want you guys to see that these are similar. Do you see that? CH3OH2 plus is the same as H3O plus. Because remember I said water is similar to an alcohol. That's why those who drink alcohol is just like you're drinking water. Does that make sense? Yes. And water is even horrible compared to alcohol because water you have two OH groups. In the alcohol you only have one OH group. You see that? So drink more alcohol and few water if you want to live longer. Say that again. Huh? No, the first step is the acid protonates the alkene. Or the alkene attacks the acid. Yes, to create the carbocation. Then the alcohol now comes in. And then now you have to regenerate your acids. Does that make sense? I'll be in my office if you guys want more exercise, if you guys want to have fun with mechanism. I have a nice whiteboard in my office. That whiteboard is made for you, not for me. It's not made to decorate my office. It's for you guys to come over there and write your mechanism on the board while I'm doing something else. You guys write your mechanism on the board. I want to see that board dirty. I will buy more I will buy more markers for you guys to use. Okay, I will have more markers for you guys to use.